So in terms of media formats, right, that's what the name of the module is. It kind of really sells itself in what it does, right? So you might be thinking, what's that all about? It's about formats of media. That makes sense. Now, I will bound that in a minute and give a bit of top and bottom to it, because it's not just about any old format. You know, we're not going to be diving into old analog vinyl and stuff like that. It's just completely out of scope. So what this module really becomes is a module about how compression works, which I think is awesome. Again, love this module for that reason. So it's really where all of the big hitters and real clever people with the past in computer science have made media and the way that we know media work. Like, a lot of the culture that surrounds what we do today is because of this stuff. And I'll go through that as we go through. So in a short sentence, I suppose, what is this module? It's about compression. It's about how compression works, which I think is, like I say, is extremely important. Also, it's about some operational stuff to do with how we have different formats of media and interchange formats, and how we pass it around and archive formats and all that kind of stuff. So stuff that we do with different formats in order to use them for different purposes, and where the strengths and weaknesses lie. It's media formats in the sense that it's, you might be thinking video formats, and when I say compression, you might be thinking of a compressed video, but it's also images, it's also audio. So all of those things are all contained within this module. And in order to give it some bounding, I suppose, I mean, here's a rough timeline of different formats that have come about. We've got the old school stuff. There's a YouTube link. I'm not going to click there, so feel free to find that later on, about recording on tin foil and old wax, what do they call them, wax cylinders. Those were also all the old sort of formats of how to record audio, and obviously audio came first in terms of recording techniques, and then later on we managed to record video and make video cameras, which is kind of cool, and obviously stills cameras came in there somewhere too. A lot of that history I'm not completely all over, but important stuff all the same. And then somewhere, I love the vagueness of these. I didn't actually design this slide, but I love it's like 1927 and then 80s. So somewhere along there, digital came along, right? So computing techniques, and we've already discussed how awesome digital is last year in computing and networking. And you can tell I'm a proponent of the digital thing, because digital and the techniques involved in digital, moving away from analog, democratizes that technology. So it allows you and I to do this stuff. Well, you and I probably would already have been doing it anyway because we're these kind of nerds, right? But it allows your nan to do this stuff, which is kind of incredible, really. So along came digital. We had DAT, so digital audio, CD, Betacam, SD, you know, all this kind of different kind of rough formats, things that are digital formats. Then we had CD, minidisc, DVD, and HD came along in the 90s. And what you'll notice around here, sort of a little bit here, but around here, all of a sudden we've got iPod, MP3 players, commercial HD, so stuff landing on things, mobile phones and the progression of those. This is where compression came in. So this is where we're going to start to do our work, all right, where this is. The work we did last year was talking about uncompressed audio mainly, because we talked about sampling theory. Uncompressed video is basically the same thing, it's just pixel values, right? So it's quite simplistic and we didn't dive into it too much. In this module, we're going to dive into, with a lot more detail, how this sort of compressed world came along. And if you look at the culture shift here, I think it really is quite revealing. If you look at 1980s, you've got DAT and CD and Betacam, SD. You know, these things are much more like professional formats, really. Like obviously there is stuff that is commercially available to normal humans, but from this point to this point, it goes from stuff that you would buy and put in a rack down to stuff that goes in your pocket. And that's the cultural shift. And that's why I think this is so important. And then obviously we've got the more, the newer formats, I suppose, stuff like 3D, whatever. We've got 4K, which I think this thing is, or, you know, 4K/UHD. We can discuss that a little bit. We've got high frame rate, HDR, all those things have come along. And to be honest, the standards have got a bit messy and horrible since then. I think at some point in this era, we forgot how to make standards, and then all of this stuff is a mess, generally speaking. But, you know, knowing about this mess is where we come in, really. And you've got things like Netflix, mobile phones, and that kind of progression. There. Cool. So all that stuff happened, right? So compression is an enabler. So, I mean, this is a silly thing. Has anyone watched Silicon Valley, the comedy TV show? It's okay. But the funny thing, or the thing about that, is it's all to do with a bunch of dudes that are coming up with an app, and they accidentally make incredible compression. So the idea of taking data, throwing away loads of it, and still keeping something that you need there is a really important concept, and that's what we're going to be doing. But in terms of an enabler, it enables, like I say, lots of cultural shifts. Mobile media, so everything that happens on your phone, all that kind of stuff, requires compression. It doesn't stay uncompressed for very long. It requires RAM, basically, in order to kind of compress as it goes, but all of the files, generally speaking, on your phone and all that stuff is in a compressed format. Audio, not so much, but, photos and video. It really enables cloud storage and that kind of interplay now. Like I say, your nan has access to this stuff. She's probably got like an iCloud account or whatever, and all of a sudden you've got somebody that can make film, It sounds silly, but this is something that in the 90s, this was like exceptional. People having access to filming devices. Obviously technology's moved on, but the fact that you can now grab all that stuff and you have effectively infinite storage and you can just sling it up in the cloud, that isn't really possible, even with today's bandwidth and storage lack of limitation. Even with those wide open storage capabilities, it still requires compression to be feasible. And so I put it's basically an effective bandwidth amplifier. We are now getting to the point now, we're getting 5G that's sort of slowly, limply rolling around in this country. The bandwidth, it might be fast in terms of its theoretical maximum speed, but the actual effective bandwidth that anyone in person gets is obviously a bit wanky still, because lots of people are on that particular channel. So we still have quite slow internet connections compared to some parts of the world. I've just gotten excited a minute ago because I got a phone call from a fiber company that are willing to install to my house, finally. So I might actually get some fast internet at my house because I'm currently on fiber to the cabinet, which is fine, but I kind of want stupid fast. And so, we're slowly getting there. But that's only happening now. And obviously, phones and all that kind of stuff have been happening for years. So compressing the media and compressing the data that we're sending becomes a real bandwidth amplifier. We get a more effective bandwidth when we're compressing the media we're sending. And because of that, like I say, we've got this culture of media capture now. Things like what we called the Web 2.0 movement is all because of this. So Instagram, social media, all of those things came along and are suddenly massive in people's lives. Entire economies are built around this stuff now, purely because we have the power to move data around, big stuff. Streaming is an obvious example. Streaming doesn't happen if it's uncompressed. Pure destruction of physical media and the kind of subsequent destruction of property ownership, which is a bit of a pain, has kind of come along with this. So nowadays we just rent everything. I guess a big example of that would be the recent Steam admission that none of us own any of the games on Steam. We're just being allowed to play them. Thank you very much. But the idea of ownership over this media now doesn't really exist as much, which is a negative of the technology. Like, we have to discuss the negatives. But the idea that we don't have to store a massive DVD collection, you've probably all had or seen big stacks of CDs. Like, back when I was younger, everyone had a tower of CDs this big, and lots of people had 4 of them. Like, that was just their collection. And obviously not taking up that space is quite an obvious thing. Archival stuff, so having a compression system that compresses efficiently allows you to archive more information. And all of this becomes what I like to call democratization of technology. So the idea that with the technology that we develop as media technologists, we've democratized filmmaking or music creation or any of these things. Like, the access to this stuff, like I said, just in the 80s, which feels a long time ago, but it isn't really. It was only professionals that could access this stuff, and all of a sudden we have everybody doing it. So I think it's a big deal. That's what I'm trying to say. This module, I think, and it's the reason I continue to build it into the degree. It's an awkward one to teach because it's very specific, but it is what it is. So indicated teaching plan, this is what we're going to do over the weeks. At least that's what I've set out. And I'm I'm going to give anybody that comes into this module free rein to do what they want to do with it, though. So I'm going to give them this indicated teaching plan, tell them that we've seen it, but I've also will tell them that it may change. So introduction is what we're doing today, and talking about formats generally in terms of categories of formats. Talk about lossless coding, so how to code things and throw away information but not actually lose anything. seems like magic, but we do and can do that. Then we're going to talk about psychoacoustics. So the idea behind psychoacoustics and thinking about that is what can we hear and what can we not hear? What are we not particularly good at hearing? If we know that stuff, we can throw away information that lives in those areas. And that's what, as a spoiler, that's what MP3 is. We basically go through a file and we say, right, what can we not hear? Let's bin it. And that's how we manage to make savings in MP3. So that's MPEG audio, MP3. Then we're going to talk about other audio codecs and what we've built since MP3, basically, so all those ones. Image compression, so talking about how we compress images down and make them smaller without losing too much. Talk about MPEG video then, so take it from images to moving video and what happens in the middle there. And then talk about contemporary video codecs, so that's stuff like AV1 and all those ones that require GPU hardware now to crunch on. So we'll talk about those. And then adaptive streaming, and then talk about how these formats are used in industry. Lots of stuff to do with like mezzanine formats and when you pass things around in a TV studio and all that kind of stuff. And then we'll also have some time to talk about DRM. And again, this is indicated, like from me talking about this right now, that not all of this is written, so it'll be a little bit as I go. All of this stuff goes on forever. Like as far as I know, this module has been in the program for at least 20 years. But I'm sort of tweaking it as we go. So that's the indicated thing. So that's what we're going to go for to start off with now. You will notice 2 is missing there because next week we've got the Sky trip that I was advertising out about. So I won't have a class on next week. It's one of those things. I don't know how to get around it really. There's only one of me, and so we have to go and do that. So next week we just won't be on. After that we'll catch up. We'll have plenty of time to catch up though. So that's the plan. Assignment. Again, I don't want to pin this down too much because I am quite insistent that someone's going to take this module. I was never supposed to be teaching this thing. As time has rolled on, we've obviously got super late in employing someone, which is really frustrating, but it's meant that I'm here doing this. I would like you guys to see a few more people so that it's not just me all the time, to be quite frank about it. So it will be very guided by whoever the new module leader is, but when we validate a degree, which means we put it together, we have to put the details in there. And the details that we have to stick to basically say that it's going to be a technical support report, which is a mouthful, which is a format-based issue of some description. So it's kind of like, oh, there's a tech support issue that's happened about formats in some way. And so there'll be a scenario based around that, essentially. So it's going to be a 2,000-word report on that. Now, I was quite surprised about that, in a way, because there's a classic thing that we've always done in this module, which is where you used to have to make a teaching thing. Teaching about MPEG video. And that must have been dropped at some point, and I've not had eyes on this module for a few years, but on our last revalidation, which would have been 5 years ago, we must have dropped that in favour of this thing. So it's something different compared to what I'm used to, but that is what it'll be. So I can't give you any more details than that because I don't want to pin the next lecturer into something that they maybe don't want to do. But it will be around that. Some kind of issue has occurred and you need to document and propose and document a solution to it. It will be something to do with compression, obviously. All right? Happy? So that's that. So we've got a brief thing to talk about today. And then we'll dive into something and do a little bit of work. And then that's us done for today. If I can find the buttons. Okay. So we're going to talk about formats, the different categories of formats basically. And you would have probably heard some of these words before. And if you've ever done any video or audio work, you probably would have saved in some of these formats because obviously we're mostly talking about digital formats, and on the main, we're talking about file formats. Like, obviously, we do talk about sort of transmission in a sense, but because of the way that IP works, it's file formats anyway. So we're talking about file formats here mostly. Ooh, look at that. It's got cheesy animation. So, media is available in a lot of formats. We're focused on compressed digital. That's where we live. We've covered uncompressed, and I'm happy we know enough about that, really. So we're going to be talking about compression in digital formats. So to start us off, I don't know if you guys have got any opinions. What does a media format mean to you, and what are some media formats that you can think of? Yeah, I did. Yeah, true. But in terms of file formats, I talked very much about like physical formats. Oh, there's a lot of them are physical formats. MP format, yeah. MP4, JPEG. WAV, uncompressed, but yeah. Or kind of compressed. It's a bit complicated, that one. Yeah, so stuff like that is what we're after, like, you know, file formats. So, in terms of categorizing them then, and we have to start to like open our understanding a little bit about this. There are compressed formats and uncompressed formats. We would typically call something like WAV an uncompressed format. There is some, obviously we are putting it into a format in such a way, and there is, I think there's a small amount of compression there, but it's essentially just describing the samples. So it's an uncompressed format. So that's a big thing. A big file. No matter what you do, they turn out to be big. Especially when you talk about video and you talk about high bit rate video. So if you talk about high like color accuracy on a video, so bit depth basically, then those files get massive. The other categorizations are lossy and lossless. Anyone know what the difference is there? Yeah?
Sort of.
Go on.
One's where they like take out pixels. If it's like a photo, like you take out pixels for to make the file smaller.
Yep.
Can't remember the other one.
So you lose, it's fine to say you lose something. So if it's a lossy audio format, you lose some of that something. It could be frequency information, it could be bit, you know, it could be dynamic range, it can just be something. Depends a lot on the format as to what it is. But the point there is that if it's a lossy format, it means you lose something when you compress it. And then, which seems natural, right? Most compressed formats we think of as like JPEG, and you know if you keep JPEGing the shit out of something, it gets worse and worse and worse, and it doesn't look good anymore. And that seems very natural to us. We're compressing something, we're losing information out of it, it gets worse. But we also have uncompressed formats. And uncompressed formats, lossless formats are compressed. They are smaller than their original counterpart, but they also look or sound or smell exactly the same. And one of the magic things that we're going to dive into is how to manage that. We've also got containers. Have you come across containers? You will have done. Have you ever, well, the classic example is if you ever do a bit of like video editing or something like that and you try and like push something out as an MP4 and you've got like some files on your computer and you load an MP4 and it works, and then you load another one and it says that the codec's not supported. And you go, well, they're both MP4. The reason for that is those two things have a different codec in them. They are both container formats. So container formats basically ambiguate away from the idea of standardizing on a specific codec or whatever. They have stuff in them. They're like boxes, containers. We'll talk about them a little bit more in detail in a sec. There's also raster and vector, which is an image, a couple of image terms. Anyone come across those before? Vector images? Do you know what they are? No? So raster images are like pixels. So a JPEG or a PNG or anything like that, when you load it up, it looks great. When you zoom in, it goes pixely because you're zooming into the individual pixels.
Does that mean that vectors are just what makes up that image and not the actual pixels itself?
Kind of. So vectors are mathematically described images. So what you tend to do is use things like Bezier curves, which is like I have a straight line, I can curve it, and then there's some maths that apply to that, which means that once that's there, you have a path. And if you zoom right in on that path, it's still fine, perfect, because it's just describing a path. So you can zoom right in on vector images, and they are infinitely zoomable, which is good. Again, we'll discuss a little bit more in a sec. There's a couple of slides. So. Then there's these are not categories really, but there are kind of like thought processes. There's high compression, high compute codecs out there. So there are some codecs that are very high compression that still give you very good results. The downside of them is that you need a ton of computational power to encode and decode them. And that's the more modern formats that we'll see, like say AV1 and stuff like that tend to fit into that category. They do a very good job. They are very psychovisually appealing, but they take a ton of computational power, which means that you need a dedicated graphics processing unit, a GPU, in order to do those things. And then there are sort of low compression, low compute ones, which are still useful in today's world. If you think about the set-top box that's on a TV, or the built-in processor in a smart TV, it may be very low compute, and so you have to pass it a lower compression, lower compute codec. So you have to kind of trade off between those. And what we're getting at here is that no single format obviously covers all of these use cases, right? There's loads of different places where we might want something that's very high compute because we need to squeeze it as much as we can. If we've got high compute capabilities but low bandwidth, we might end up leaning in that direction. The flip side is if we've got high bandwidth and low compute, something like a smart TV that's connected to a gigabit internet connection, then maybe the compute, the compression ratio, the amount of compression squeeze that we're putting onto something isn't as important. But all of these things, we're obviously making things smaller. We're taking media and we're squeezing it down. And the process of going through this module is understanding how all of these different things come about. Yeah, so how do we do all this stuff? So to go back through them, I've done some detail on all of these. So lossy versus lossless. Lossless means that nothing is lost, which seems absurd, right? The idea that we can take something, we can squeeze it down, make it smaller, and then when we decompress it or uncompress it, it gets back to where it was before. And what we mean by lossless is that it gets back to bitwise identical media. So what we mean by bitwise is if we take a file, and if you think about computer science like we've done last year, you can describe that file, obviously it's being described to the computer in ones and zeros. So you're going to have a header at the top which really describes what it is and what the computer needs to understand from those ones and zeros and what order they're going to be in and all that kind of stuff. And then if you just look at it in terms of its binary, it will just be a shitload of ones and zeros. If we compress something then and then uncompress it, bitwise it's the same. So every one and every zero are in the same place. And there are tools we can use to do that, to verify that. Something called a checksum will do that for you very well. Something called an MD5 checksum, which looks at the contents of a file, looks at its bits, and then does some mathematics to them and comes up with a number. And you look at that number, and if you do it before and after and compare the two, it will be the same. So a checksum is a way of us finding out whether something is the same or not. And it's often used in compression systems and transmission systems. We might want to send a file, and this is what your computer does. If you download a file, you'll download the MD5 from the server, and it will say that's the MD5 for that. And then once you've downloaded the whole file, you run your own MD5 and make sure they're the same. And if it is, you know you've got the whole file. It's all good. So that kind of thing happens all the time in networks. So we've got this compressed thing happening. The interim stage is not identical though. So when you're in your compressed format, it won't pass an MD5. But when you uncompress it again, you get back to it again. So that seems mad. How do we throw away data? But we're going to explore that in a minute. The answers will come later on, but we're going to explore some ideas around what you might think is a way of doing that in a bit, basically. Cool. And then lossy means that information is lost. Media becomes, I don't like the term, but it's true-ish, worse quality, right? And now the job of somebody that's designing a compression system is how do we decide what to get rid of? If we admit to ourselves, like if we take a bitmap file, which is an uncompressed image format, we've got pixel values, and then we have to throw it through some maths and basically get rid of a bunch of it, but we need to do it in such a way that we can't tell the difference. That's ideal, right? And that's what JPEG attempts to do. Obviously JPEG is quite old now, but it still does a great job, really. So the idea there is we're going to try and bin as much of that media as we can, but functionally give, it needs to functionally perform the same thing. We need to look at it and be pleased with the response, or the result, basically. So the media does become worse, and as we know, if you keep compressing images, for instance, they do get worse and worse and worse. But how do we decide what to get rid of? Can we try to decide to get rid of information that we perceptually don't need? And that's where the term psychovisual and psychoacoustic comes from. Well, that's why we're diving into psychoacoustic and psychovisual principles. So if we can decide, for instance, that when an image is very dark and then you've got like a color next to it that's also very dark, our eyes can't often see it, well, why don't we just bin all that information? Which is basically what a lot of these things are doing. Or, for instance, maybe we decide that at a certain resolution, everything's too small for a person to really be able to see. Why don't we bin that? Or why don't we do some things that make it so that we have less accuracy in those areas? And that's basically what we do. And what we're aiming for is it is a lossy file, yes, but we're aiming for it to be perceptually lossless, which means that if I put a bitmap in front of you and I put a JPEG in front of you and you can't tell the difference, is it really, well, I mean, it is lossless by definition, but is it really, really lossless? It's perceptually lossless. And while we're on this subject, sampling is a lossy process, if you think of it. It's an uncompressed, lossless format that we bring it into, samples. But by sampling something, we're losing information. And we talked about this last year when it came to the audio examples we gave. We said, well, you know, if we're going to sample at 44.1, that means that we're going to get a functional 20 kilohertz of audio information into our file. Well, we've lost everything that's outside there. So it is a lossy process. We've lost information. But most of the time, we don't need it. So a lot of this stuff is very much involved in the context of what we need out of our media. If it's just for people, we don't need it. If you're recording bats and you want to then downsample it so you can hear it, it would be lossy in a way that would be, bad. So we have to be careful about what we're doing. Cool. Now, we talked about containers very briefly, but here's a bit more detail. Sometimes they're called wrappers, and containers, as we kind of alluded to earlier, are not codecs. So things like the .mov format, the .mp4, MKV, if you've come across that, and the one that's used in industry quite a bit, MXF, those are file containers. They are file formats, they're media formats, but they are ambiguous as to what codec they are, right? So they have a list of codecs they support. So MP4, for instance, will say, right, I support bing, bang, bing, 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 these ones. And so you can kind of determine, if you wanted to support MP4 as a file format, you have a list of codecs that you would need to build into your program to support that. But upon opening any one of them, you don't really necessarily know which codec is inside it. Yeah. So that is a bit of information that is quite confusing for most normal users of these files, especially if you're on a phone and it's recording something and you're saving it as an MP4 and then you pass it to someone else and then their system doesn't have that codec. It feels very strange to you. But yeah, the ways in which you code it is ambiguous. File formats or file container formats are still quite important to us though. Now the big advantage, that's obviously a massive disadvantage, right? But the big advantage of them is it allows you to have a container that can have multiple essences within it. So you might have multiple video streams inside it or multiple audio streams. You can have a German version and a Swedish version and all these different versions of the audio. You can also pack that thing full of metadata. So you can have in there anything you like, really. It's a very open kind of format on a lot of these containers. But things like subtitles are the common metadata. So you're really putting subtitles along with something, and you may have found it's very common when you're doing like piracy, basically. If you pirate things off the internet, they've often come in a nice package that's got 6 different subtitle formats in it. You can have audio description and accessibility features like that. Like subtitles, I suppose, is an accessibility feature, although it's used more than that these days. But yeah, containers contain bits and bobs. And all the audio and video, the actual stuff that we want to keep in there, or the important stuff, the audio and video content, is what we call essences. So inside a container format, we have essences, and those are audio and video, generally speaking. Now, obviously, standards being standards, they are also forward-thinking. They can also have like haptic information in there. There's nothing stopping you doing that. They can have 3D worlds and stuff like that in future formats. So we do have to think about essences as a little bit more than audio and video, but in functionality, they are just audio and video these days. So MP4, MXF, MKV, a whole bunch of other standards. PDF is one of these, which if you've ever really messed about with the details of PDF, you may have found that annoying already. If you've exported a PDF from something like Word, it's very clumsily doing that and trying to get through that. PDF is a container format. The container format can contain the fonts that are used in it. So you can say include the fonts and put them in there. Or you can do take those fonts. The person doesn't need them because they're not going to edit them. So convert them into paths instead, and then it becomes vector paths. So you take all those strokes and paths and you turn them into you take the fonts and turn them into strokes and paths, which makes it into a vector image, which then stops it being machine readable. So, it's a difficult thing. And understanding these formats, like I said, I think that's important. I would say that most degrees here that have media as an output should understand this stuff. You know, any degree that has a PDF as an output should understand this stuff. It needs to be machine readable. What does that mean? Why is it not? Well, there's loads of information there. PDFs also support, by default, they're vector, but they also support raster images as well. And they support vectors, but then they also give you a raster preview sometimes. So sometimes when you load PDFs into Word, you get the raster preview, which is a low quality thing. Lots of pitfalls. And in terms of raster and vector, we said about this a bit before, but raster is basically pixel values. You make up a picture. Vector images are mathematical rules, so they're literally lists of let's make a curve. It uses these mathematical rules in much the same way as you make curves in physics and maths. So you have advantages and disadvantages of both. Vectors are very bad for JPEGs, basically, like photos. Anything with like a lot of detail, or if you want like pixel by pixel detail or something, they're very good for like things that have got lines and shapes, things like logos, symbols, and text. They do that stuff like perfect, basically. If you ever look at one of those, you can zoom right in. You know, the glyphs in the text get massive, and that looks great. But they're really pants for things that are complex and basically images like photos. Whereas raster is the opposite. It's great for that. But obviously the disadvantage is it's not infinitely zoomable. There are packages out there that will convert from raster to vector by trying to find lines and paths and draw them in there, but it always looks stupid. It looks cartoony and just bad. If you have an infinite amount of paths, you're basically describing pixels and you get back to raster again. So, you know, there are disadvantages and advantages of each. So this kind of thing is exactly why, if you've ever come across people using the Adobe program Illustrator, it's because that is a vector package. It's designed to make vector images. So people using Illustrator will be using it because they're making logos and graphics and HTML, you know, stuff for web. They won't be using Photoshop. Both of them support both, annoyingly, but you know, Illustrator is designed to be raster, vector-based, sorry, and Photoshop is a raster image editor. Okay, so it's really important to know these differences. Like, if somebody's asking you for a logo, and you supply them with a shitty rastery one, then they might print your logo in. If you're a company and you're sponsoring something, they're going to blow it up massive and print it. It's going to be all pixely and gross. Like, understanding these things from a design point of view is useful. Whatever job you go into, that's important to me. It doesn't have to be a media job. It doesn't have to be a broadcast or live events job. It's anything. I think that's important. People screw it up all the time and it annoys me. You can tell. Cool. So that is that bit